Hello everyone, my name is Qiyi. I'm a postdoc researcher at the University of Liverpool. The paper I'm going to present today is Approximate Bisimulation Minimization, and this is joint work with Professor Stefan Kiefer at the University of Oxford. The model of interest in this paper is labeled Markov chain, or LMC. So there is an example LMC on this slide. Each LMC has a finite set of states, a finite set of labels, a probability transition function, and a labeling function. So in this example, we have 5 states, and each state has a label. So for all the LMCs in this talk, the labels are just the colors of the states. From the orange state, with probability 1/3, it goes to the left part, and with probability 2/3, it goes to the right part. It is easy for us to see the symmetry between the left part and the right part. So in probabilistic model checking, such symmetries could be employed so that we could minimize the state space of the system by merging the states that are probabilistic bisimilar and to tackle the so-called state explosion problem. So if we minimize the labeled Markov chain showing on this slide, we will end up with an LMC with only 3 states. So imagine now that we have another LMC which is very similar to the previous one, but the probability of the transitions differ by a positive small number epsilon in the right part. Then the left part and the right part are no longer probabilistic bisimilar. So S1, T1 are not probabilistic bisimilar. In this case, if we minimize the system by merging the states that are probabilistic bisimilar, we will end up with exactly the same LMC that with 5 states. We could analyze the system using another notion called probabilistic bisimilarity distance. It's a notion to measure the behavior similarity between states, and it is a number between 0 and 1. Distance 0 coincides with probabilistic bisimilarity, and the smaller the distance is, the more similar the two states behave. So if we compute the probabilistic bisimilarity distance for this example, we find that S1, T1 have a probabilistic bisimilarity distance 1. So any minimization algorithm that would like to merge states with small probabilistic bisimilarity distance wouldn't work for our example. And there's another notion called approximate bisimulation, could also be used to analyze our system. And it is also a notion to measure the behavior similarity between states. And this approximate bisimulation has this nice property that with a number k, any k-bounded linear property has similar probabilities in a pair of states that are approximate bisimilar. But this notion has a problem that is it is quite expensive to compute. So for our LMC, S1 and T1 actually are half epsilon bisimilar. So in practice, sometimes we are given LMCs that are with transition probabilities that are not known exactly or perturbed or can only be obtained by, for example, sampling, but we still would like to compute approximate quotients such that They are similar to the original system, and they have small state space. So here's a picture to illustrate our goal. So we are given this LMC and another LMC M prime with perturbed transition probabilities, and we would like to compute approximate quotient, we call it Q, such that these approximate quotient and the exact quotient of the original system have a similar size. Next, I'm going to formally define approximate quotients and present you the minimization algorithm to compute such approximate quotients. The definition of approximate quotient is given an LMC, M. S is a finite set of states, L a finite set of labels, tau is the transition probability function, and L is the labeling function, and an epsilon. An LMCQ is an epsilon quotient of M if and only if there is another LMC M prime and Q is the exact quotient of M prime. And M prime has to satisfy this condition that for all states, the probability distribution over the successor states in M and M prime have small L1 distance that is less than or equal to epsilon. And since tau prime, the choice of tau prime is not unique, there might be multiple epsilon quotients of M. And our question is it possible to find an optimal approximate quotient? An optimal approximate quotient is a Q star that has the minimum size among all these epsilon quotients of M. And as this next theorem suggests, it is unlikely that we can have an efficient algorithm, a polynomial algorithm, to compute such optimal approximate quotient. The theorem states, given an LMC, M, epsilon, and a positive integer k, the decision problem whether there exists an epsilon quotient of M of size k is NP complete. It is NP hard even for a fixed k is 5. And the hardness is from the subset sum problem. Since it is unlikely that we would have an efficient algorithm to compute optimal approximate quotient, we won't aim for computing such optimal approximate quotient of a minimum size. So before presenting our minimization algorithm, I would introduce you two important properties of our approximate quotient. So the first one is related to approximate bisimulation. Let Q be an epsilon quotient of M. Then for all pairs of states S and SQ, S is from M and SQ is the corresponding state in Q. Then we have that S and SQ are half epsilon bisimilar. They are approximate bisimilar. So since for all these pairs of states, S and SQ, they are approximate bisimilar, they will inherit the nice property that any linear time property that depends only on the first k labels has similar probabilities in these pairs of states. And the second property is this additivity property. So consider three LMCs, M1, M2, and M3. And M2 is an epsilon 1 quotient of M1, and M3 is an epsilon 2 quotient of M2. Then we have that M3 is an epsilon 1 plus epsilon 2 quotient of M1. So this additivity lemma could be applied as our minimization algorithm, which will be introduced later, successively computes a sequence of approximate quotients. So at the beginning, we have this LMC. Then we compute exact quotient. We call it Q0. We run our minimization algorithm. We get an approximate quotient Q1. And we run our minimization algorithm again. We get Q2 until we get an approximate quotient Qi. And if we know that each approximate quotient Qi is an epsilon quotient of Qi minus 1 for all I, then by using this additivity property, we know that Qi is an I times epsilon quotient of M. And next, I will provide the details of this minimization algorithm to compute the approximate quotient. The algorithm to compute the approximate quotient is very similar to the well-known algorithm to compute the exact quotient. For both algorithms, the first step would be to obtain a partition. So let's first recap the exact partition refinement for computing an exact quotient. The input is just an LMC. And at the beginning, we have this partition x0 where all the states are in the same set. Then we enter a loop. We increment the loop counter I, and we split each set in the previous partition such that for all states in a set of the new partition, we have that they have the same labels and the probability distributions over the previous partition are the same. And we repeat until we reach a fixed point. That is, we can no longer split a set in the partition. And the first step of computing approximate quotient, that is approximate partition refinement, is very similar to this exact partition refinement. So we have an extra input that is a compression parameter epsilon. So at the beginning, we also have all the states in the same set. Then we run into a loop. We increment the loop counter, and similarly, we would split each set in the previous partition so that for all states of a set in the new partition, they have the same label. But we won't require that the probability distributions over the previous partition are the same. Instead, we require that the probability distributions over the previous partition for all the states in the same set have small L1 distance that is less than or equal to epsilon. And we repeat until we reach a fixed point. To compute exact quotient, we already have a partition X by running this exact partition refinement. And the next step would be to compress the state space. What we do is to treat each set in the partition as a state. Then we set the labels for all these new states. And we have a new transition probability function. The probability from E to E prime, so two sets in the partition, is said to be the probability from S to E prime, where S can be an arbitrary state from E. And this is because for all states in E, the probability distributions over X are the same. And now we have an exact quotient of this LMC. So to compute approximate quotient is very similar, but we have an extra input, compression parameter epsilon, and our output would be an approximate quotient. So we get a partition by running our approximate partition refinement. And then the next step would also be to compress the state space. So we will also treat each set in the partition as a state, then we set the labels. However, since We do not have that for all states in a set of the partition, that the distributions over the partition are the same. So instead, for the probability from E to E prime will be said to be the average probability from S to E prime over all states S in E. And these now we have the new the labels, and we have the transition probability function, and we can output this LMC as the approximate quotient. And we have proved in our paper that actually these LMC would be an epsilon quotient of the input LMC. Now let's see a simple example of running our minimization algorithm on a simple LMC. And this is the LMC at the beginning of this talk. And let's set this compression parameter to be 2 epsilon. So we first run this approximate partition refinement. And at the beginning, all the states are in the same set. Then we get x1, the partition where the states are grouped by their labels. S1 is with T1, S2 is with T2. At this point, since the probability distributions over x1 from S1 T1 have L1 distance 2 epsilon, which is equal to the compression parameter, and similarly, the probability distributions over x1 from S2 and T2 have L1 distance to epsilon. So we just reach the fixed point and we get the partition x1. And now we would compress the state space and we will get this final LMC with only 3 states. So this is a very simple example. In our paper, we do a lot of experiments on LMCs that are more complicated. These LMCs are taken from the model checker Prism and the model protocols and the randomized algorithms. What we do is for an LMC from Prism, we add some noise to the transition probabilities and we get this perturbed model M prime. We compute the exact quotient of the original LMC, and we also run our minimization algorithm successively to get a sequence of approximate quotients. So there are 2 parameters we can tune here. One is the noise, the error parameter that is added to the transition probabilities. And the other one is the compression parameter that is an input to our minimization algorithm. So what we do is then to compare the size of the final quotient Qi and the exact quotient of the original LMC. So on the slide shows the experimental results for an LMC that models the contract signing protocol. So the original LMC has more than 74,000 states and 75,000 transitions. Then we compute the exact quotient of this LMC. We get an exact quotient with 992 states and 1,027 transitions. Then we perturb this LMC by error parameter 0.001. And we run our minimization algorithms using various compression parameter epsilon. So we can see from these highlighted rows, so when this compression parameter epsilon is greater or equal to the error parameter 0.01, the final approximate quotient has exactly the same number of states and number of transitions as the exact quotient of the original system. On the right is the table showing the experimental results for another LMC which models Hermann's self-stabilization algorithm. The exact quotient of this LMC has 612 states and more than 100,000 transitions. We then perturb this LMC by an error parameter 0.0001, and we run our minimization algorithm using various compression parameters epsilons. As can be seen in the row highlighted in yellow, when the compression parameter epsilon is 0.01, the final approximate quotient has the same number of states and the same number of transitions as the exact quotient of the original system. But if we increase the compression parameter further, as can be seen in the row highlighted in pink, when the compression parameter is 0.1, the size of the final approximate quotient is much larger than that of the exact quotient of the original system. In our experiments, we find that for most of the LMCs, if we set the compression parameter to be a little bit bigger than the error parameter, but not too big, then we can successfully recover the structure of the exact quotient of the original system. With this, I'd like to conclude this talk on approximate quotients and the minimization algorithm to compute such approximate quotients. Thank you for